Did you see the Blackboard video? Okay, good. So everybody so far has seen the rest of the lecture. So if that's the case, then we can move right into review. Let me see how many more we're missing. I'm counting 4. Missing translations. 3 more. Okay. In that case, we can go ahead and look at the review, since everybody's seen the rest of the lecture. All right. So we're going to, next exam on the 21st is going to be on Chapter 6, Thermochemistry. And question?
What? No, I'm just staring blankly. I'm tired.
So we need to look at some specific problems. First of all, like I always do, has anybody got a specific problem that we need to deal with so that we don't miss it? Because once I start talking, we might blow right past it and, you know, get your questions answered. Okay, come on in. Did you see the rest of the video?
No, how about my mom's house and video that one?
Okay, so you haven't seen the last part of the lecture.
No, but when I get back to that, let's kind of watch it.
Okay, we'll just start with the review then. All right. Let's see, where to begin? Oh, anybody have any problems we need to deal with? Okay. We'll look at number 1's a good place to start. On the review document. So it says that a gas absorbs 0.0 joules of heat. So remember the term for heat is Q. And the amount of heat the problem gives us is that. So we're just tallying the information that's given from the problem. And then the gas performs 30.7 joules of work. Now, remember our sign convention. If this is the system, that's the surroundings. Everything is referenced to the system for the sign purposes. If heat goes into the system, it's a positive sign. If heat leaves the system, it's a negative sign. Same thing for work. If work is done on the system, it's a positive sign. If the system does work on its surroundings, that's a negative sign. So back to the problem. If the gas performs 30.7 joules of work, that means it's working on its surroundings. That means
Negative.
Exactly.
So would it be negative 30.7?
Yes. Now we got that correct. Let's see what the question is. Change in internal energy of the gas. Okay, so we need a formula. So the change in internal energy is equal to whatever heat transfer takes place plus the work that's done. Okay? So now all we have to do, that's the thinking part. The rest of it is just plugging and crunching numbers. Q then is 0. And work is minus 30.7 joules, right? So that means the change in internal energy for that system is 30.7 joules. And if you look at your possible answers, 30.7 is D, a negative 30.7. So we put that positive 30.7 in there because if you don't watch your signs, you can think that's the right answer when it's wrong. Okay, so signs are very important when we're dealing with work and energy transfers. Questions about that? All right. Take the easy ones first. Okay. Better mark this one so I don't try to do it again. Okay. So what types of energy are possible? This I'm referencing two, but I'm going to talk about it a little bit before we do that. What types of energy? How can we subdivide energy?
Kinetic and potential.
Exactly. So potential energy could be what type?
Stored up.
It could be stored. Well, it could be stored in bonds, or it could be due to position. Those are the two main types. In other words, if you're in a gravitational field, then the higher you are away from the center of that gravity, the more potential energy you have. Right? So if you move from this level to that level, you've stored some potential energy due to your height. Okay? And then, of course, in a chemical reaction, if you have, say, reactants yield products like that, then if you put energy on this side, then that means energy is going in as a reactant and it's stored in the products. Right? So it has to be stored in the bonds of the products. But if you, and that, by the way, is an endothermic reaction. But in an exothermic reaction, energy is part of the products. So that means you have energy released over here. Where did it come from? It came from inside these, right, as a product. So that means these two together have less energy stored in them than these two. Okay, that's potential energy. But this problem asks us about kinetic energy. So what are we given? Let's see, we're given mass, 1.56 kilograms. Right? And it's moving at 94 kilometers per hour. So the velocity is 94 kilometers per hour. Okay. So we have that information, and the kinetic energy we can calculate by that formula. 1/2 mass times velocity squared. But remember, in order for the standard unit here of joules to be your answer, these have to be in SI units as well. And what's the SI unit for mass? Kilograms. Okay, we're good there. What's the SI unit for velocity? Meters per second. That's not meters per second. Okay, so that has to be converted. So we go back to our conversion factor practice from chapter 1 or 2, one of those, I can't remember. So hours is in the, and of course, when you do these conversions, if you have a quotient or a product or multi-unit as part of your starting point, you do 1 unit at a time, convert it, then convert the other one. So let's start with kilometers. So we got to get rid of kilometers and end up with meters, right? So how many meters are in a kilometer? Right. Okay. So meters is taken care of. Now we need to do seconds. We've got hours on the bottom here, we need hours on the top here. And either you know or you don't know, but you could say, if you only know minutes per hour, then you can go chain them together. Right. So that takes care of hours, minutes, and we're left with seconds. Okay. Now, once we get that answer, we'll have the right units, and then we can plug those values into the formula. All right, so let's see. This is 1,000 divided by 3,600. And then times 94. So I get 17.78 meters per second. Now we're good. We can say 1/2 mass, 1.56 kilograms. And then our velocity with the proper units. Squared. Don't forget the square. Don't forget to put it in there, squared, and then don't forget to do it when you calculate. I've seen both of those done on exams. All right, so 1.56 and divide by 2, and then 17.78 square it. So I get 240, let's see, 3 significant figures, 7. Now, the units here would be kilogram meters squared per second squared. Okay, right. Kilograms times meters squared divided by second squared. Because that propagates through not just to the number, but to the units. And it just so happens that kilogram meters squared per second squared is equal to joules. Okay. Now, is that one of our answers? Oop, I don't see it. What did I do wrong?
I was wondering how you got 17.78 out of that.
Yeah, that's a good question.
That's what I was confused.
Okay. Let's do it like this. That's because I've got the wrong answer. Is that what you got?
Yes.
Okay. Now what do we get? Let's square that one. So now I get 532. Is that one of our answers? Well, actually, all the answers are in kilojoules, aren't they? So if that's joules, how many kilojoules is that? Move it this way, right? Kilojoule is a bigger unit.
5.32.
Right, 1, 2, 3, 0.52 kilojoules. Or I think the answers are in scientific notation. 5.32 times 10 to the minus 1. Yep. Okay. So let's see if we can do another one and I don't make a mistake this time. Check that one off. Let's see. Okay. Here's a thought problem. 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process? And pressure equals 1 atmosphere, temperature equals 370 K. Okay, so here's the process that we're asked about, going from gas to liquid water. And they're telling us it's exothermic, right? So where's the energy go?
It goes back to the beginning.
Exothermic. It's giving up energy. Right? Exothermic is always on the right-hand side. Okay, so if the gas is giving up energy to make liquid, so here's our system, and the system is composed of the water. There's the surroundings. If it's exothermic, right? Oops, not G, Q. That means Q is negative, right? And W. So what's happening as you go from a gas to a liquid? Say you have a piston here, and it tells you got 1 atmosphere pressure. Okay? And the temperature is held constant at 370 K. So we don't have to worry about the temperature. It's not changing. And the pressure is also constant. So that means as you have water gas going to water liquid, what's happening to the volume in there?
Linearized.
Going from gas to liquid?
Volume's
Oh.
down.
Yeah, volume is going to decrease. So that means work is being done on the system. As the volume decreases, that means this pressure is being applied constantly.
So it'd be a positive.
Right. So W is positive in that case. Sometimes it helps to draw pictures. Question?
So H2O gas is the system, but if it's working on the liquid part of it, how is that?
No, it's working on the gas
Oh,
because it's going from gas to liquid. It's working on the, well, all of the water is the system, but once it gets to liquid, the pressure doesn't matter. Pressure only matters on the gas. So the gas is being removed into liquid, and that means the pressure applied is being applied on the system.
oh, okay.
Okay? That one did take a little bit of thought, didn't it? Okay. Let's see. Let's try. Let's try number 7. Okay, what's given? 1 mole of an ideal gas, okay? Is expanded from a volume of 1 liter to 8.93 liters. So initial volume is 1 liter. Final volume is 8.93 liters. Pressure is constant at 1 atmosphere. Okay. How much work is performed on the surroundings? So it's already telling you. As it expands, it's doing work on the surroundings, right? And there's a formula for that, isn't there? Negative P delta V. It should be in useful information. Let's check. Sure. Yeah, there it is, lower right-hand corner. Okay, so that's the work that's being done on the surroundings. And once you know that, all you have to do is calculate what's the change in volume. So the pressure is 1 atmosphere. And the change in volume is final minus initial. Right? So the final is 8.93. The final, no, excuse me, final. That's right. Initial is 1 liter. Right. So this is going to be a positive number. This is a positive. That makes it negative. So it's negative 8.93 liter atmospheres of work. Let's see, does that answer the question though? 7. No, because the answer is in joules. All right. We have a value for work, but we need to convert that to joules. Right. There's a conversion factor that should also be here in useful information. And let's see, where is it? There it is, about the middle of the second column. 1 liter atmosphere is 101.3 joules.
Well, am I answer your question?
Sure.
So do you not subtract 8.93 minus 1 to get 7.93?
Yes. Obviously. And somebody's awake in this class. It's not me. I had a professor who used to say this in regards to statistics. He used to say, it ain't necessarily so. That just means there's always a small error here. There's always a small probability that what I'm telling you is wrong. In this case, there was a large probability. Okay, so now we have 7.93 and 101.3. So that's 8.03 times 10 to the second joules. Is that one of our answers?
Did you make sure it was negative?
Yeah, it should be negative.
All right.
Okay, it's given in standard notation. Right. So the answer is going to show up like this. All right. This one is a little involved. Do we want to do that one? Number 9.
Yeah, that's the one I was looking at too.
It looks like it's worth tackling. All right, so we've got a fuel-air mixture is placed in a cylinder fitted with a piston. Okay, the original volume is 0.3 liters. And the question is, what's the final volume? All right, so we're given an initial volume of 0.310 liters. Final volume is the question. What else are we given? We're given Q is 935 joules released. And the pressure is constant at 635 millimeters. Okay. Checking myself. Okay. This is going to have to be converted to atmospheres. Okay. So that's, and is 0.8355. Why do I have to do that? Because with this gas, when it expands, we're going to be measuring things in terms of liters and atmospheres, not in terms of joules. So if we're going to do a calculation of work by that gas, then this has to be in atmospheres and this has to be in liter atmospheres.
So it would be like from Morgan's lab work.
No, not yet. I do have one in here with a gas law. But this one, all you need to do is convert this to liter atmospheres. 101.3, right? Or is it the other way around? That's right. That many joules per liter atmosphere. Okay. So let's see. We'll do that calculation. 935, change the sign, and 101.3. So this is negative 9.23 liter atmospheres. Okay. So if the problem, let's go back to the problem. How much work is performed on the surroundings? So the work is going to be negative. W is going to be a negative value. Just as a reminder. There's our formula again. We know what the pressure is here. 8,355 atmospheres. And then we have final volume minus initial volume. Okay. And the work that's done, oh, here it is, minus 9.23 liter atmospheres. Okay, so there's your work, and there's pressure, there's volume change. So now the thinking part's done. We just have to solve for that final volume. Right. So this is going to be negative 9.23 liter atmosphere equals minus 0.8355 times final volume. A minus times a minus is a plus, so 0.310 and 0.8355 gives us 0.2590. And this is liter atmospheres. Right, now we'll put this one on this side, and as it comes over, it becomes negative, so it's actually, it makes this one more negative. So it's this one plus that one with a negative sign. Let's see, let me just put that, just change that sign.
Negative 9.484.
Yep, negative 9.489. That's good enough. And that's a negative 0.8355. Yep. Now, the final volume is this one divided by that one. Let's see. So I get 11.4 liters. And if I didn't make another mistake.
That's it. That's it.
Okay. All right. Mark that one on the list. What about, starts with 14. Good. I didn't put an explanation for that one, so maybe we better do that one in class. 14 through 17. Okay, these are the conditions. Let's see, a gas in a 1 liter bulb at standard temperature and pressure. So the volume of the gas is 1 liter. Standard temperature and pressure. What's standard temperature for a gas? 273. 0 degrees centigrade. Okay. And standard pressure is 1 atmosphere. Okay. Okay, so those are the conditions that are given. Now we have questions. So the first one, what's true about the value of Q? Oh, wait a minute. It's connected to another bulb. I left that part out. What happens when the two open? Okay, so we need a picture. There's your valve. And there's the gas at these conditions. And this one, the only difference between this one and this one is this one's at 0 atmospheres. It's evacuated. Okay? All right.
Will be equal to 0. When the gas is just.
Okay, so what's true about the value of Q? When you open the valve, what's true about Q? So here are our choices. Greater than 0, equal to 0, less than 0. More information is needed. Or none of these. Right, so if it's all at the same temperature,
It would be the same.
Q would be 0. There's been no heat change at all. Temperature being held constant means that there has been no heat transfer at all. How about W? Well, in order to measure W, well, first of all, hold on a second. What's the system? The system is the gas, right? So every place that the gas is now and will be is inside the system. Maybe this will help. And these are the surroundings. There you go. Right, so whatever happens inside the system stays in the system. This is Vegas. Whatever happens in here stays here. So there's been no change in Q, there's been no change in W. How about internal energy? Well, if these don't change, delta E can't change either. How about delta H? So we didn't, I got to this discussion in the video, I think. The only time where Q and delta H are equal is when pressure is held constant. And the pressure is constant at 1 atmosphere. So Q would also be 0, it'd be the same as, delta H would be the same as Q. Okay. Plus delta H and delta E are state functions. So it doesn't matter what happens in between. In this case, nothing happened in between.
So would they be equal to 0 or?
They're all equal to 0. And it all depends on identifying this as your system and these are the surroundings. That being the case, they have to be zero. Because there's been no transfer of work or energy across that barrier. It looks like a good question for an exam. Let's do 18 while we're here, since we got our mind in that gear. So energy, we got these three terms to deal with: energy, work, enthalpy, and heat. How many of these are state functions? Well, I just told you actually. How many are, well, let's just identify which are the state functions and which are the path functions. Which ones does it matter where you go in between?
Work and heat.
Yep, that's a path. This is a path. This is a state. This is a state. So it doesn't matter for these two, it doesn't matter what your path is, how you get where you're going. But these, it does matter. Right. Okay, let's go to 19. All right, which ones of these are intensive properties or intensity factors, I call them? So there's mass, temperature, volume, concentration, and energy. We want to know which ones are intensive properties. What do I mean by that? That means it doesn't matter how much of the stuff you got. The property is constant. If you change the amount of the substance and the value of one of these changes, then it's a capacity property, capacity factor. All right, so which ones are intensive?
Temperature.
Temperature, right?
Energy.
Energy goes up and down with how much you have. How about
Constant.
concentration? If you have 10 milliliters of 1 molar hydrochloric acid, you just sucked it out of somebody's stomach. Or if that small person, if you have a bigger person, they got a bigger stomach, and you suck out 100 cc's or milliliters of the acid, it's 1 molar, still 1 molar. Doesn't matter how much you have.
Concentration is still the same.
Yeah, concentration is the same. Temperature would be the same. Mass is not, because depending on how much substance you have, the mass will change. Volume changes with how much you have, and energy changes with how much you have. Okay? Oh yeah, C, Roman numeral 2 and 4. Okay, let's see, what about this one? Anybody can propose one from the floor.
We do 22.
22. All right. All right, here we go. So we're dealing with the combustion of ethanol And let's just write it up here. That's the business end right there. That's what makes you feel funny after a while. And that yields 2 carbon dioxide. This is a gas. And 3 water. And the delta H, this reaction is minus 1.37 times 10 to the third kilojoules. Okay. So what do we know? That's abbreviation. Let's be consistent. So the enthalpy of this reaction is negative, which means it's exothermic. Right? Energy is leaving. Here's our system. Energy is leaving the system. It's a negative number. Negative enthalpies are always exothermic. Okay, so back to the question. Which of the following is true? 1. The reaction is exothermic. That's true?
Yeah.
2, the enthalpy change would be different if gaseous water was produced. Let's see, enthalpy is different if yes, in this case, when you're given a reaction with states, the state of the reactants and products has a bearing on the enthalpy. Right? Why? Well, let's think about water in particular. If we ended up with water gas over here, that gas would absorb some of this energy. It would not be released. It would take some energy to keep that liquid in the gaseous state. So that would change this value. Because we know that that process is endothermic. It absorbs energy to take a liquid to a gas. That's a positive value. Combined with this would give you a less negative value. So yes, the delta H would be different. How about 3? Reaction is not an oxidation reduction, not redox. Have we seen the change in oxidation states? What's the oxidation state of oxygen? 0. Elements are all 0 oxidation state. So where's oxygen over here? In a compound, there and there, which means it's -2 here, -2 there. So you have an oxidation state change for oxygen from 0 to -2. Right? Carbon changes too, but it's easier to attack it here. If you have an element on one side and that element ends up in a compound, then it is redox. Also, any combustion reaction is redox reaction. That's another rule of thumb you can go by. So not redox, that's false. Let's see, in 4, the products of the reaction occupy a larger volume than the react. Product volume is greater than reactant volume. Well, know. Oh. Products, okay. What determines volume as long as temperature, pressure, and temperature and pressure are constant, then you only need to know the relationship between moles and volume, right? We're holding the temperature constant, we're holding the pressure constant. So which side do you have more moles of gas? Liquids don't count. So there's 2 moles of gas here, 3 moles of gas there. So you started off with more moles of gas, didn't you? Right? So it's actually the other way around. You have more reactant volume than product volume. Okay? That's Avogadro. That's what he said. One is directly proportional to the other. You got more moles, you got more volume. As long as you keep these two constant. Okay, so the only two that are true would be, oh, energy. Sorry, left out energy. No, that's the wrong problem. Too many Roman numerals. That's it. 1 through 4. So the answer to that was A. Roman numeral 1 and 2. Are you bored yet? Yeah, he's bored. That's a good thing. If you're bored working chemistry problems, then you are working enough of them. If you're not bored, stiff, and you haven't done enough of them. And of course, that means you've done enough of them to get them correct. That's an implied condition. Okay, any others? You're on time, 9. Let's see. Almost 22. Where is that one? I was looking at one just a second ago. If I can find it. I need to know the specific heat capacity. 51. This is a good one. So this is talking about the specific heats. Or specific heat capacity to be correct, of these metals. So we've got zinc, magnesium, iron, silver, and lead. And the values are 0.387, 1.02, 0.237, 0.127. And the units here are joules per gram degree centigrade for each one of them. Okay, so we can compare apples to apples. So the question is, if the same amount of heat is added to 25 grams of each one, so the mass for each is 25 grams. Each one has the same mass, right? So that eliminates this term, right? Because they're all the same. Grams, they're all 25 grams each, right? So now we're comparing what happens when you add heat to them, what happens to the temperature part. So remember what I said about quotients. Anytime you have a quotient of units, you have a direct proportion. other words, this is a constant value. If that one goes up, that one goes up. Okay? So, it doesn't tell us, does it tell us? Okay, the same amount of heat is added. Their starting temperature are same. So they're all starting at the same temperature. What we want to know is which one has the highest final temperature. If you add the same amount of heat, right? So what does this mean? Let's start with this one. If you add 1.02 joules of heat for every gram, the temperature rises 1 degree centigrade. If you add that same amount of heat, 1 joule, then it rises twice as much, because it only takes a half of the joule to raise the temperature 1 degree. Then you stick the other half joule in there, it raises it another degree. So what's the trend? The smaller the value, the higher the temperature for the same amount of heat, right? So if you know that, which one of these would have the highest final temperature, right? One with the smallest specific heat capacity. That's interesting. Magnesium has the same, well, actually it's slightly higher specific heat capacity as water. Water is 1. The magnesium can hold a little bit more heat for the same change in temperature. So if we ever run out of water, we can just, cover the earth with magnesium. Not, because that's not everything that water does, right? As far as heat capacity goes, yeah. Look for a planet that's covered in magnesium. If you're looking for life, right? No. Okay, so that's the answer. That one will have the highest temperature for the same amount of heat added. We can do that mathematically, right? We could say the amount of heat is equal to the mass times the specific heat capacity times the change in temperature. Okay? So if this is constant, this is constant, and the temperature here is a constant minus the variable there. Oops, wrong way around. Okay. So this is constant. That means we only have to say, how do these two vary? Right? So we've got this one. Q is equal to S times T final. And these two vary. Right? So now we have a product is equal to a constant. So what do we say about products equal to a constant? They're inversely proportional. Right? So if this one goes down, that one goes up. There's two ways of looking at the same problem. Okay. '52 is a good one. I want to be sure. We might want to do something else before we get to 52. Yeah, let's do 50. Back up one. Okay, how much heat is liberated at a constant pressure when 2.35 grams of potassium metal reacts with 5.868 mils of liquid iodine monochloride? and it gives you the balanced equation, right? If the equation's not already balanced, of course, you got to do that. But the purpose here is to work on thermochemistry, not balancing equations. So with the limited time available in an exam, you're going to get the balanced equation. Okay, and the delta H with a little zero, what does that mean? Standard conditions, standard temperature and pressure. That means right there.
So that means it'd be two.
And other standards. Like if you have concentrations, that would be standard, be 1 mole or 1 molar. So the value is 740.71 kilojoules per mole. All right. Now let me see if I need to explain that. Remember when I said enthalpy for an equation is for the entire equation. Some instructors I've seen like to say per kilojoules per mole of equation. That's a little too, that's a stretch for me. Right? That's a whole mole of an equation, right? I just say that value in kilojoules is for this equation. If you're focused on this one, it's per 1 mole, right? 1 mole. If you're focused on this one, it's per that 1 mole. If you're focused on this one, it's per 1 mole. If you're focused on that one, it's per 2 moles of potassium. See what I mean? Okay. So let's get back to the question. How much heat is liberated? So what we really want to know is what's the delta H for the reaction when we're given these conditions. 2.35 grams of potassium. Okay. And 5.68 milliliters of liquid iodine monochloride, and the density is 3.24 grams per mil. Okay. So we can't convert mils into moles. Remember, we can't go anywhere in this equation and answer the question until we have moles. So this has to be converted to moles. All right, so we might as well make grams first, right? So if density is this, density equals mass divided by volume, right? So we've got the volume here, and if we multiply volume, bring volume over here in the numerator, it cancels out milliliters here. So what we need is mass equals 3.24 grams per milliliter times 5.68 milliliters equals how many grams? I get 18.4 grams of that one. Now we've got grams and grams. The next question you have to answer is, you've got a definite amount of that one and a definite amount of that one. So the light bulb ought to be ding, limiting reactant. Which one runs out first? We have to convert this to moles. Right, so we need potassium is 39.10, so 2.35 grams. 39.10 grams per mole is equal to what? 2.35 and 39.1 is 6.01 times 10 to the minus 2. Okay. Question? Oh, the funny thing about Zoom is when it hears something from one of the participants, it pops you up as this big image on my screen and gives me a ding dong. So, oh, but it wasn't you. There's Zach. What's Zach? Oh, yeah. The other Zach. Is he there? I see your name, Zach, but I don't hear your voice. No response. Okay, let's go back to me. Okay, so now we have this many moles of potassium. How many moles of iodine monochloride do we have? Well, we need a conversion factor. So iodine is 126.90. And chlorine is 35.45. That's 5, 13, 12, 162.35. Okay. So we divide that into 18.4. And I get 1.13 times 10 to the minus 1. Moles of this one. All right. Now, how do we find the limiting one? You remember? You say, I hear something. Is that Zach? The way you find out which one's limiting is you assume for the moment that all of that one is used up. What amount of product does it give you? And then you assume this one is used up completely. How much product would it give you? Compare the two, and the least amount tells you which one was limiting. Right? So, this one is that many moles of iodide monochloride, and these are 1-to-1 ratios, so this value is the same value for those two. Right? Just pick one, KCl. 1-to-1. So that means 1.13 times 10 to the minus 1 moles of KCl would be produced. Like an R. Would be produced from that much iodine monochloride. How much KCl would be produced from this one? Well, we multiply it by K on the bottom, KCl on the top. What's the ratio? 1. Right, 2 to 1. So half of that, 3.055, right? Times 10 to the minus 2 moles of KCl. So which one's the least? This one. Let's see if I'm still on the right track here. All right. So if we're saying that this amount of heat is evolved for this equation, and we base it on 1 mole here, this is equal to 1 mole of KCl in this case, then we've already figured out 1 mole of KCl, or the moles of KCl. We can use that in terms of KCl because that means kilojoules per equation, and this is kilojoules per mole of KCl produced. Okay? So that means now all we have to do is multiply this times that value. Kilojoules per mole of KCl. So let's see, do I still have it in here? Let me flip here. There it is. Okay. Divided by 2 gives me that number. Actually, that's this right? 601. Yeah. 3.055 and 2 times 740.71. So I get 22.6 kilojoules, negative 22.6 kilojoules for that reaction with those conditions. And okay, what are the units? Right, the units are in kilojoules, but it's scientific notation.
So it'd be
So it'd be minus 2.26 times 10 to the 1 kilojoules. What's the nearest one to that? D. Right. D is the nearest one to that. So there was a rounding error in there somewhere, either here or when I was doing the problem. Okay? That takes a lot of work and requires that you think about things that we've already covered. First of all, you're given the reaction, right? So that's no big deal. Understand what delta H means. Then look that you have 2 amounts of reactants. So one of them is going to run out first. And in order to compare them, you have to be able to calculate in terms of a product. How much product is going to be produced. So that requires this to be converted to grams and the moles to moles. Then moles of product. Moles of product compare, and you find out which one's limiting. Then you can use that with your enthalpy to determine the heat of the reaction. So it's multi-step. I'll give you that much. So you have to be very methodical, right? If you try to sit down and just splash it on the page, what you'll get is modern art, which is crap anyway. Did I say that out loud? All you have to do is go to New York City, the Modern Museum of Art, and you'll see a whole building full of crap. Okay. Now, one place that I would advise going, Smithsonian.
yeah.
Oh, yeah. There are lots of buildings in the Smithsonian.
Mm-hmm.
So give yourself,
Little compartments in the basement and everything.
give yourself a lot of time. Or if you only have a part of a day, be selective. Right? What do
Or
you
be hustling through there 1 or 2.
what do you like most? You know, I like Air and Space Museum, so I hit that one for sure. And I went over to Civilizations, whatever's in that building.
Yeah, and then you got to see the Hope Diamond while you're there too.
Oh yeah, yeah.
You definitely got to see that while you're
Oh yeah. Got to see the Hope Diamond. Okay. So any questions about that one? So let me see. Let's do a calorimeter experiment. I think that's what we need to do. $52. Okay. got to pay attention to this one, because we haven't discussed how to determine the heat capacity of the calorimeter. You need to know that for your lab today. Let's see how we doing on time. 9:20, and we go to
Like 10 something.
10:30. Okay, we're good. We'll have time to discuss the lab ahead of time. This is number 52. Okay, the heat of combustion of benzene, and the reaction doesn't matter. But this is benzene. All right, and we're just going to burn it in a calorimeter. And the heat of combustion we're given is minus 41.74 kilojoules per gram. And for this particular experiment, we're going to have a mass of 2.82 grams of benzene. We're given the change in temperature, so we don't have to do before and after. Change in temperature is 3.29 degrees centigrade, and that's an increase. The temperature's going up. What's the heat capacity of the bomb calorimeter? All right. So, actually, well, the pressure is constant, so we can say this. Right. Delta H for that reaction is equal to Q, which is that. All right, so remember when I was discussing, did I discuss calorimeter? I must have done it in the video, right? Yeah, I think I did it in the video. So your calorimeter is an isolated system surroundings. Right? So your calorimeter is going to be, well, that bomb calorimeter is going to be a little bit different than a styrofoam cup, because when you combust that in a calorimeter, they call it a bomb calorimeter because if you don't construct it correctly, it'll go off like a bomb because the pressure builds up. But your calorimeter is completely isolated from its surroundings. Right, so you got your calorimeter, you got your thermometer, right? You might have a stirrer in here. And then your reactants are in there. But it's isolated from all its surroundings. That means matter cannot cross the barrier, heat cannot cross the barrier. That's why we make our bomb calorimeters in this lab out of styrofoam, because it's an insulator, a good insulator. So the reason I'm banging on that point, it's isolated. Whatever happens in there stays in there. So remember when we said all those things were 0, 0, 0, 0? Everything that happens in there has to add up to 0. All the heat changes equal 0. So what are the heat changes that are going to take place? Well, you're going to have the Q that's assigned to the combustion. Right? Combustion of benzene. And then you're going to have a Q factor for the calorimeter. Right? The calorimeter might be isolated from the outside, but the calorimeter has a heat capacity. It will absorb some heat if it's an exothermic reaction, or provide some heat if it's an endothermic reaction. Right? So you have to compensate for this value in order to determine what that one is. So the question in this one is, what's that one? We want to know what that value is. Okay. All right, so what is this value? Well, the amount of heat generated by 1 gram is this amount. Right? So the amount of heat here is actually this mass times that value. Because that's in kilojoules per gram, so grams cancel, and we get so many kilojoules. Right? And it's negative, so it's being evolved from the reaction. But in our calorimeter, it stays there. Right? So it's going to affect the temperature, only we're not interested in that right now. We're only interested in what's this. So the Q for a calorimeter in general terms is a calorimeter constant times the temperature change. So what does that mean? If this is joules and this is degrees centigrade, what does this value have to be?
Q over.
Joules over degrees centigrade, right? For these to cancel and leave that one, right? So the units of this one are going to be joules per degree centigrade for your calorimeter. Unlike specific heat capacity, which is joules per gram degree centigrade, or joules per mole degree centigrade. We have both types. Okay, so that's a distinct difference between this one and that one. This one is an intensity factor. This one is a capacity factor. The size of your calorimeter matters. What it's made of matters. How much of it that it's made of matters. So the reason I'm saying that is, once you determine the calorimeter constant for your calorimeter as you're constructing it, don't change anything. Don't use a different thermometer. Don't change a cup or lid. Don't change a stir. You got to keep the same stuff in there because you're determining the calorimeter constant for that construction. If anything changes, then that value changes. Okay, so now we get back to this. So in order to find the calorimeter constant, there, that's an unknown, we multiply it times the change in temperature, right? So the change in temperature is 3.29 degrees centigrade. And that should cancel this and leave us with joules. So joules here, kilojoules there. All right, so we have a unit discrepancy. This is going to be in terms of joules. This is in kilojoules. So how many joules is this one? It's 1,000 times that, isn't it? Right, I multiplied 1,000 times that. I did it in my head. Let me show you what I did. 41.74 kilojoules. We'll just take the kilojoules part. If we want to change that to joules, just take away the K. K means 1,000. Put the 1,000 out here. Okay, we took that K and put it right there. Put this times that. Then I reduced it to scientific notation in its proper format. There. Okay? I thought I might have done a flyby. So I better explain it. That's a good way to approach a problem, is look at the units. If you can extract a part of that unit out here, Then you can leave that one behind, convert that one to a number. Okay, so now we have the proper units, joules, and this is going to be joules. So now we have our equation set up. We just multiply this one times that one. 2.82 grams and 4.174. I'll change that in my head. Minus 1.177 times 10 to the 5th joules. That's our combustion value for the benzene. Now, this value is still 3.29 times that value. Okay? So, and this is degrees, see? So now we need to put this one on this side, right, which would make it positive, 1.177 times 10 to the 5th joules. And then, I do it in one step. Put that 3.29. So we move this one over here. Now we can divide both sides by 3.29. Okay. And 3.29 divided into this value. 3.58 10 to the 4th joules per degree C equals the calorimeter constant. Don't miss. Now let's see if I made a mistake. 2. Oh, I left it in kilojoules. Well, okay, we can convert that to kilojoules. You know, we probably could have left it kilojoules, couldn't we? Yeah, we could have left it kilojoules. I was assuming that the answer was going to be in joules per degree C. So what would that be? Take 10 to the 3rd here and put it right there as a K. Right? So I took 10 to the 3rd out of there. That left 10 to the 1st behind. And that 10 to the 3rd became K. And then I think the answer is in standard notation, so it'd be 35.8. So that's your calorimeter constant. For this reaction. We good? Okie doke. So the moral of this story is, what happens in the calorimeter stays in the calorimeter. It's isolated. Everything that happens in the calorimeter adds up to 0. Okay, let's see what else we can find here. Oh, we haven't talked about Hess's law yet, have we? Let's try. Let's do 60. What is Hess's law, by the way? it says the enthalpy of a reaction depends only on starting and ending conditions. There's another way to write that. Or another way to say it is, the enthalpy of a reaction equals the summation of several enthalpies of reactions. So what that means is, if you have a reaction that you're investigating, and you want to know the enthalpy of that reaction, you don't actually have to do the reaction to find out what it is, using a calorimeter and all that method we used before. If you can find a summation of individual reactions that have their standard enthalpies given, and you can rearrange them some way, add them together, then the summation of the enthalpies is equal to the enthalpy of this reaction. Right? So you can take a reaction, well, this example. Let's do this example. I'm going to have to erase that because I'm going to need a lot of room. Your book probably gives it to you differently. I was trying a practical approach. So if we're given, this is our target. This is our target equation. CrF3, which is what? Chromium 3 fluoride. Right? That's a solid. And we want to react it with hydrogen chloride gas to yield chromium 3 chloride solid plus hydrogen fluoride gas. Notice I didn't say hydrochloric acid or hydrofluoric acid because they're not in water. Right? As a gas, that's hydrogen chloride and that's hydrogen fluoride. Okay, so we want to know what's the delta H for that reaction. But instead of doing the reaction, we have this information that's available. Reacting chromium with HF gas yields plus 3H2. And the delta H for this one, I'm going to put it up here like this, is minus 691.4 kilojoules. Okay? Let me write the second one down here because we want to manipulate these reactions. So this one reacted with hydrogen chloride gas yields this one plus this one. And the enthalpy of this reaction is 59.2 kilojoules. Okay, first rule of using Hess's law. when you add these two equations together, they have to be that one. There's no ifs, ands, or buts about it. If you can't rearrange these some form or fashion and add them together and get that, then you cannot add the values there. So first thing you do is look, see what's on what side, right? CRF3 needs to be on this side. And that puts HF over here where it's supposed to be. Okay? So you have to flip the equation. Make that the reactants, and these are the products. Okay? So you do this. CRF3 plus H2. Let's see, that's the gas. And then this one comes out on this side. What happens to that? You're running the reaction backwards, aren't you? So you change the sign. Now, whereas this was an exothermic reaction, this one's now endothermic, right? So it's 691.4 kilojoules. That's positive. Now, the other thing you have to look at is the balancing part. So you've got 2 here, and you've got 6 here, but you only need half as much, right? So you take the whole thing, including the enthalpy, and divide it by 2. So now we have this one, and this one, this one, and this one. And that makes this one half of its value. So it's 2, let's see. Wait a minute. This, 3. 4, 5, 7. There we go. So now this is the one that we're going to use for that starting reaction. We're going to use this one. Now we need to check this one out. All right. So is it oriented correctly? Reactants and products. Well, this has got chromium on this side, but that's okay because chromium's over there. Remember, when you add equations together, if you got something on this side in one and that side on the other, they cancel, as long as you're the same magnitude. So let's focus on this one, right? It's on the right side, reactant side, and this one is on the right side. But they're too big, right? They're twice as big as we need them. So this one has to be halved. And you can check yourself as you go. Yep, there's 3 HCl. That's good. And half of this one, right? So that gives us one of those. And half of that one. Now what happens to this? Well, it's still a negative because we didn't flip the equation, right? But we need half of it. Right? So 2 into 5 is 2, 2 into 15 is 7, 2 into 19 is 9, 2 into 12 is 6. Okay. So these are the two. Those two are the ones we're going to add together. Okay. So since I'm limited on space, let's focus on these two and say what reactants and products are on opposite sides. Right? This one, right? There's chromium solid, 1 and 1. That one cancels. Okay. How about this one? HCl. Nope, there's no HCl over there, so we got to keep that one. Chromium 3 chloride, excuse me. Chromium 3 chloride is not on that side, so we keep that one. And HF. Let's see. H2. Oh, okay. H2. I'm missing. Oh. Oh no. Nobody caught me. Right? Change this one. Divided by 2. Okay?
It's the one they cancel out because there was one right there.
There's one here and there's one here. So they cancel. Let's constantly do a reality check. Okay, now we can add them together. There's this one right there. Let's see, this one. And then that one's gone. We got this one. Okay, and on this side, we got, let's see, this one. And this one. Now, is that the reaction? There, there. Yep, we got the right reaction. Now that means that we can take this value and this value, add them together. $345.7. And negative 279.6. So I get 66.1. And that's positive kilojoules. So the overall reaction is endothermic. Now, $60. I got papers and utensils lying all over the place. Yep. Okay. Does everybody see that?
So for the 66.1 kilojoule, you just added that one up there
This one.
to the bottom.
Yep. For this one, we had to flip it and cut it in half. For this one, you just had to cut it in half. And this proves that what we did was correct, because when you add them together, that's what you get. It's your target. So whenever you're presented with a problem like this, you look at the equations that you're given. I'm thinking in terms of an exam. The equation, your target equation, what is it? It should be balanced, but you might want to check it just to be sure. Then you look at the given equations that you can use to create this one. You may not need all of them. You want to pick the ones that have the correct components in them. First of all, it doesn't matter what side they're on. Are they there? Then when you start manipulating them, you want to be sure that you end up with the correct reactants on their proper side for the target. And then look at the amount of each one. Now, this one, the targets, the canceled parts, you have one in one reaction and one in the other on opposite sides, they cancel. But what if you have, let's see. What if I had had something over here that was also in this one over here? Well, it cancels too. Right? So the rule still holds. If they're on opposite sides, equal magnitude, cancel. Now, if what I just did here because of limited space messes with your head, you can bring everything down and just write it all out. And then look for common elements on both sides to cancel. Do it that way. That may have been the way I did it in some of the problems too. Yeah, I think I did it in some cases like that. Particularly in this one. I brought them all down, then canceled it. Okay, let's see. Any questions come to mind? Yeah. Which one?
I'm been sitting here just looking for these. I'm gonna have to go with at least one that looks like them.
Okay.
I want to be at least like 55 and 55, 59, and which one of them I just said that kind of jumped out at me. I like 70.
Okay, let me see. Let me mark them. We're going to do 55, 57, you say? Or 59?
59.
59.
Yeah.
55, 59, and 70.
Yeah.
Okay. Okay. And we'll, of course, want to get to some further down the line. Once we get to 70, we'll keep rolling into the higher numbers. As long as we got time. So let's see, 55. Consider the following process. Oh, okay. So this uses hypotheticals, not real chemicals. So the target is this one. B equals E plus 2C. And we want to know what delta H is. We're given this one. 3B yields 2C plus D. And its value is minus 125 kilojoules. And then we're given a half A yields B, and it's a positive 150. And then we're given E plus A yields E, 350. Okay, so let's see, what are we going to need? We're going to need a B. So we got a B here and a B here. That's fine. We're going to need an E, need that one, and a C. That. So are we going to need all of them? Yeah, I think we will. Okay. So let's see, I'm going to work from the bottom up. We need to have E on that side, right? In order to do that, we need to flip it around. That's negative 350. Okay? So that gives us our E on that side. We'll keep that one. What about this one? If we put B on this side, that takes away the A, right? But we need the A on this side to get rid of that A, right? Because there's no A up here. So instead of focusing on the B for this one, we focus on the A. Got to get rid of the A here. So this needs to be doubled to get rid of that 1A. So this gives you an A yields 2B, and this one is plus 300. Now, we've got an E on that side. We've got a B on that side, but we need B on this side. So if we have a B on this side, and we've already got a D on that side, which is going to cancel this D, that's good. We've got 2 C's on that side, that's good. And we've got 2 B's here and 3 B's there, so that's going to cancel all but 1. So we're good here. Can leave that one alone. Now let's see what we get when we add them up. Right. I'm going to bring everything down. So there's a 3B on this side. There's an A. There's a D. Now on the other side, there's a 2C plus a D. And there's a 2B on this side. And there's an E and an A. And then if we add this one, and this one, what do we get? This one's going to be a negative 50 minus 175. Now let's see if our conditions are met. All right, we've got an A on this side, A on this side, D on this side, D on this side. We've got a 2C and an E, that's good. We've got 2 B's on this side, 3 B's on that side. So those two cancel and leaves us with 1. So B yields 2C plus E. B yields 2C plus E. So this value is correct. I can see where that one would throw you because this one puts B's on both sides. So we're looking at ending up with only 1 B. Okay?
So it'd be B yields 2CE plus C?
Yeah. B yields 2C plus E, which is this equation. Okay, next one was 59, wasn't it? Let's see. Yeah, 59. Okay. So our target is this one. E4H10 solid plus 6 ECl5 gas yields 10 Cl3 gas. Okay. So how many of them are we going to need? We have these to choose from. That's a minus 1, 2, 2 kilojoules. That's extremely exothermic. That's another reason for using Hess's law. If you've got a reaction that you suspect is going to be very exothermic, you might want to, if you actually have to do the reaction yourself, you might want to run through Hess's law and find out what the ballpark enthalpy is going to be. So you might need to take certain safety precautions. Okay, this one is P4.
So we're gonna do this one like we did in 55,
Uh-huh.
just switch them around and add them.
Yeah. Do you want to do it?
Well,
Okay. And this one is, or this one's even worse. Well, somebody actually had to do these. Well, you know, some of these component reactions could be the result of Hess's law also. Number 3, PCl3 gas plus Cl2 gas, PCl5 gas, and this one is minus 84.2. And then the fourth one. So these are the ones we have to choose from. We don't necessarily have to use all of them. We've got to decide which ones satisfy the conditions of Hess's law. I think I left. I did. I left an element out of this one. There we go. And this one is negative 2.857. Okay. First question. Which ones satisfy the conditions of what are our components? Well, we need P4O10. Let's see. Here it is. H. O. More errors. I think that's it. So we need this one to give us that. PCl5. PCl5. We need this one here. Cl3PO. And we need this one. I don't think we need this one because P4 is not in there anywhere. Well, it's in here. But do we have, oh, we are going to need that one. Because this one's got a P4, and we can't have P4 in the final reaction. So we're going to need all of them. Okay. Even though this one is not up here, it is in one that we have to use. So we've got to be able to cancel it out. So we've got to use all of them. All right. So let's see if I can do this in the limited space available. P4O10. P4O10, here we go. We need this one on that side and only one of them, right? So all we have to do is flip this one. And that means this one changes sign. So we're going to use this one. Okay. So now PCl5, here it is. It needs to be on that side. So we got to flip this one. But we need 6 of them. Right? So let's do it both at the same time. We need 6 PCl5. And they're 1, 1, 1. Right, so this one needs to be 6 PCl3 and 6 Cl2. And this one needs to be changed sign plus 6 times that value.
So we're in the 6.
Right here. Yeah, we need 6 of them. So 84.2 is 505.2. All right, so got that one. So we've covered that one and that one. Now we need 10 CL3PO. CL3PO. It's on the correct side, but we need 10 of them, right? So we got to multiply this times 10. And that means 10 PCl3 plus 5O2, right? 10 times a half is 5. And then 10 CL3 PO for that one. And then we have to multiply 10 times this one. So that's, we didn't flip it, so it's the same sign. That's 2857 kilojoules. All right. Now, the one we haven't used yet is this one. So we're going to have PCl3 here. And we need 10 of those. So if we multiply 10 times this one, is that going to give us what else we need? P4. Did I write those correctly?
In the first one, the PCl3 should be go 4.
First one,
There should be 4 PCl.
4 here, right here.
Yes.
Okay. I know how I did it here. I took these, put them together, and said, okay, now I need to adjust this one to make up for that. I'm trying to do it all at once now. PCl3. Here it is. That's 6. Okay, I didn't write that one correctly, did I? Yeah, I did. PCl3 is 10 here. So at least 4 PCl3. 4, 6 chlorines. 6 chlorines. So it's probably going to work like that. Yeah, I think it's going to work like that. So let's see if it does. All right, so let's see if we can cancel some things. This one, this one, this one, and that one. Okay, so we need P4O10. Here it is. All right, and that one. And then we need 6 PCl5. Got that one. That one. Now we need 10 CL3PO. CL3PO. Okay. That's this one. Now let's look at the ones that I didn't underline. There's a P4 and a P4 on opposite sides. There's 5O2. Where's a 5O2? 5O2. Okay. Let's see. Wait a minute. I got 10 PCl3s. Oh, that's okay. 6 chlorines. So do we have chlorines on this side?
Right there.
No, that's not chlorine. Here, right here. Okay. And 4 PCl3s. We got 4 PCl3s here and 6 PCl3s here, which is 10. And we got 10 PCl3s here. So those cancel. Did I miss anything? Okay, so this one canceled. This one is underlined, those cancel. This one's underlined, those cancel. Cancel, cancel, cancel. So we're good. So now we can add up this one, this one, this one, and that one. One, two, two, 5, 4, 6, 7, 2, 9, 6, 7, 3, 505.2, and 2, 8, 5, 7. So I got 610, negative 610. 16.1. That's on there. Negative 610.1. So if that one shows off the test, it better be worth a lot of points. Put that much effort into it.
You can put it on the memorization, or you can put in
Oh, the
bonus.
the required section or the
Yeah.
bonus? It looks like a bonus question.
Oh, yeah, I can memorize how to do this.
Okay, and then the next one is 70, right?
Yeah.
The problem is here, what I should have done was taken the first three, 2, 3, and 4, put them together and write them over here. Then put 1 over there. And that would be easier to see how it cancels. Okay, 70. Here we go. So we want to know the delta H of formation for PBO. Okay. Question is, what is delta H of formation, standard heat of formation for PBO solid? That's the question. All right. Based on this equation, PBO plus CO plus 1 yields then CO2 gas. Okay. And the delta H for this one is minus 131.4 kilojoules. All right. This one's not as hard as it looks. First of all, before I go to the information that's given, the equation that operates here is the delta H for this reaction is equal to the sum of the heats of formation of products minus the sum of the heats of formation of reactants. Okay, so here's what we do. This one's nice because they're 1, 1, 1, and 1. Coefficients are 1. If the coefficients are different than 1, you have to multiply those times the heat of formation for each one that you put in here. So we take the heat of formation of all elements is 0. Right? So that one's out. We don't have to put that one in. So we only need the heat of formation of CO2 and then minus the heat of formation of PBO plus the heat of formation of CO. Okay? Like I said before, if there's anything but 1 up here, you multiply that in front here by each one of these. Because the heat of formation is based upon 1 mole of each. All right, so now we're given the heat of formation of CO2 here is minus 393.5 kilojoules. And since they're all 1 mole, I'm only going to put kilojoules in there. For PBO, well, that's the question, isn't it? That's what we want to know. And the heat of formation of carbon monoxide is minus 110.5 kilojoules. Okay? Oh, and the total over here is given right there. Minus 131.4. Now we have an equation in one unknown. This one right here. Okay, all these are summations, right? Summations, subtractions, right? Like that. So we can take this one, becomes a positive over here. This one is a negative times a negative is a positive. So now it becomes a negative over here, right? So if we take this one plus this one, and then minus that one, because it's a minus times a 9, minus is a plus. Over here, it's a minus. And what happens to this one? That's a minus HFPBO, isn't it? Because minus times this one and minus times that one. So now let's see what the left-hand term is. 131.4. So I get 151.6 kilojoules. That's a positive, but this is a negative. So this value is going to be a negative 151.6. That's the heat of formation of PBO. Let's see. There it is, A. Okay? So those signs can really mess with you. You got to keep track of them. And see that this is a negative for everything that's inside there. Negative inside all of it. So let me just reiterate. What do we mean by heat of formation? Standard heat of formation of anything is determined based upon 1 mole of the compound, right? So if we were to say PBO, what does that mean? We've got the heat of formation for PBO, but what does it mean? Well, we end up with PBO under standard conditions, which is a solid. That's fixed. You can't touch it now. Any balancing you do has to be on this side, and they have to be all elements under standard conditions. So lead under standard condition is a solid. And oxygen under standard condition is diatomic gas. So how many of them do we need? We only need one of them, so we got to take a half of an O2. So that's how you would write the standard. This is the formula to calculate the standard heat of formation for PDO. Start there, work our way back over here, element, element. We only need one. So there you go. So that's what this means. That value is for this one, what we say, minus 151.6 kilojoules is the standard heat of formation for that product. Okay. So if I were to say standard heat of formation for, I don't know, let's pull one out of thin air. Acetic acid. Okay. So what do we have? We have 1, 2, 3 elements. H2, gas, carbon, solid, and O2, gas. Right. So we've got 4 hydrogens. We've got 2 carbons. And we've got 2 oxygens, that's right. So just one of those. So that would be how you would write the standard heat of formation. The formula for the formation of acetic acid from its elements. That one, that one. Okay. All right, let's see how we get it on time. Just about out. So let me take a look at what's left in this review. Unless somebody has one that's just burning your synapses up. How about 77, just for kicks. Which of the following is both a greenhouse gas and a fuel? Is carbon dioxide a fuel? You can't burn carbon dioxide, can you? No. How about coal? You can burn coal, but it's not a gas, right? So it can't be a greenhouse gas. Right? How about freon? Well, freon,
Isn't that what you put in?
refrigerator, yeah. Freon is designed to be non-combustible. So it can't act as a fuel.
Methane's flammable.
Methane.
Yep.
Methane is a greenhouse gas. In fact, methane is a couple of orders of magnitude more effective as a greenhouse gas than CO2 is. That's why they're after cows for, cows will be belching. They belch methane because they're rumen when all the microorganisms are working. One of the byproducts of that anaerobic condition in there is methane. So when they burp, methane comes out. So you hold a match in front of them when they burp, you should get a blast. Like farts, I guess. Okay. '74, '75, there are potential questions that you have to read. So everybody's reading their chapter, I'm sure. Right? Maybe not. You should be reading the chapter at least once. In fact, you should read it before you can come to class for that lecture. And then after the lecture, you gotta go home and read it again. Let's see. 59 looks like a potential extra credit. So you might want to glance at the explanation here. The only reason I'm not doing it now is we're running out of time. It's like we're getting some redundancy here towards the end. Okay, how about one last one, 98. Yeah, let's do 98 because that's a calorimeter problem that would be more like what we're going to do. Okay, let's approach this from the back to the front. Calculate the specific heat of the metal. So the specific heat of the metal is going to be something in terms of joules per gram K. Now, why did I write K instead of degrees C? It doesn't matter. It's the same size as a degree centigrade. K and degrees centigrade are the same size degrees. It's just the 0 points move. So K works just as good as degree C. But don't let it throw you. If I had put degrees F, yeah, that's a different story. Okay, so that's our target. That's what we're looking for. And we lost our, oh, no, we didn't. You magically came from here to there. Okay, so we're given the mass of the metal is 36.2 grams. Its initial temperature is 81 degrees centigrade. And it's dropped into a calorimeter containing 50 grams of water. So that's the mass of the metal. And the mass of water is 50 grams. And the specific heat of water is 4.18 joules per gram degree C. The heat capacity of the calorimeter is 125 joules per K. And the final temperature, we're also given that, is 29.7 degrees. Now, what am I missing? Oh, the initial temperature of the water. This is the temperature of the metal. This is the temperature of the water. They're two different temperatures they start at, but they end up at the same temperature, right? They equilibrate. So we use this one as our final temperature for both calculations, or for all calculations. And this value, here it is. Water starts out at 21.7 degrees C. Okay, that's a lot of information. But here's what you do. Everything has to equal 0. Right? So you got the Q of the calorimeter. And you got the Q for the metal. And you got the Q for the water. All those changes have to add up to 0. So what's the Q for the calorimeter? Well, it's going to be the change in temperature times this value, right? So it's that for the calorimeter times the change in temperature for the calorimeter. The metal is going to be a different story because we're using an intensity factor here. We don't know what this is. That's the question. The specific heat capacity for the metal, right? times, and this is going to be in joules per gram degree C. So we need the mass of the metal times the change in temperature for the metal, then the water. So the specific heat of water is given, 4.18. The mass of the water is given at 50 grams. And the change in temperature for the water. Okay, so that's the equation symbolically. Just notice the difference between this one, and that one. That one's because this is a capacity factor. This is an intensity factor, which requires those factors to reduce it to joules. Okay, now we can plug in the numbers. So 125 joules, 125 joules. I'm just going to change it because it means the same thing, right? I just said that. So that times the change in temperature. So what's the change in temperature for the calorimeter? Well, the calorimeter, typically what you do is you put the water in first and let it come stabilize temperature. That means the calorimeter and the water are both at the same temperature, starting and ending. So you can use the final temperature here for both the water and the calorimeter. So it's 29.7. 29.7 minus 21.7 degrees C. Okay. Now we have this unknown times its mass, 36.2 grams, times change in temperature. So what's the change in temperature for the metal? Well, the metal starts at 81 and ends up at 29.7. So the final is 29.7 minus the initial 81. Okay. There we go. Now for the water. So water is 4.18. I'm not going to write the units in. And the mass of the water is 50 grams. And the change in temperature for water is final, 29.7, minus initial, 21.7 is initial. It's the same as the calorimeter. There we go. Now we've done all the hard thinking. We just need to solve this unknown. Might as well do it because this is the same topic we're going to be doing in the lab anyway. I assume. 10:30? Yep. Yes.
For the middle of the equation, the 29.7 minus 81.
Yep.
Why are you using? You probably already said it. Didn't catch it. Why are you using the temperature of the final temperature of the water for the metal?
Because they all come to equilibrium.
Oh.
Right. The metal's in contact with water, and which is in contact with the calorimeter. So at the end, they're all at the same temperature. All right, so 0 equals this one, 29.7, that's 8 degrees, isn't it? So that's 1,000 joules. Then we have this one there, and then times, that's 29.7 minus 81 is minus, this is minus 51.3 times 36.2 which is minus 1857 joules. And then this one is 8 times 50, which is 400 times 4.18. That's 1672. There we go. So we've got this term and that term. On this side would be negative 2672. And then this would be minus 1857 times S. Okay. Everybody with me so far? I did a couple of things at once. And then we just divide this into that, negative into negative, so value is going to be positive. Let's see. 2672. So I get 1.598. And that would be joules per gram degree. Is that right? 98. Yeah, I made a miscalculation somewhere.
I have a question.
Yep.
You subtracted 1672 from 1,000.
Add them together,
Oh, you added them together. Why?
because that's positive and that's positive.
But are you gonna put 1,000 on that side? Oh, wait, never mind.
Yeah.
Yeah.
Then they both become negative.
I see.
So that's not where my mistake is. My mistake was someplace else. 8 times 125. 1,000. About 36.2. And is this 51.3? Yep. 5, 7, okay. And that one, let's see if I made that one right. 1672. Okay, so those are right. See if I did this one right. 2672. 1857. Oh, that's where I made my mistake. Punched it in wrong. 1.44. 98. Yep. A for 98. Okay. So now we need to take a look at the lab. I don't know if it'd be better to talk about it in here or in the lab. Talk about it in the lab. That'll give you a break. So take a break, go in the lab, and I'll be right behind you. Go to your bench when you go in there and look at that water that's on the heater and see if it's boiling yet.
Oh, it is.
Yeah. Let's stop this one.